Hello, my name is Michelle and welcome to my channel where we solve the LeetCode problems together. If you are preparing for technical interviews or simply want to improve your problem solving skills, you have come to the right place. In today's video, we'll be tackling problem number 70 and I will be walking you through the thought process and the technical skills needed to arrive at the optimal solution. We will be coding the solutions in Python, so make sure to have your editor, your IDE, or the LeetCode platform ready. So grab a cup of coffee, get comfortable, and let's dive into today's problem. So for today's problem, before we go into the coding part, let's first go through the problem description. From the description, we can say we are imagining we have a staircase with a certain number of steps, and what we need to do is we want to reach out to the top, but there's a catch each time. We can only climb 1 or 2 steps. So how many distinct ways can we climb the stairs? That's exactly what we'll be figuring out in this problem. This is currently a very classic dynamic programming problem with many applications in computer science and beyond. So there's nothing like special here. It's currently if you have ever recorded the problem 509 we discussed yesterday, this one would be very familiar with that. Probably the only difference is due to the background story, but the idea of the whole solutions are almost the same. So you may also want to have a try to test if you really understand what we discussed yesterday by pausing the video and trying to write the codes by yourself. As I'm recording this video by solving this problem, I will just count for 3 and we will start just coding. So ready? 3, 2, 1. Okay, let's get started and get ready to flex your problem solving skills and dive into this problem. So before still a little things we want to do. So let's first refresh the core idea behind the dynamic programming, which would be just to break a complex problem down into the smaller sub-problems and solve each sub-problems only once. Per se, for this example, we're going to say how we climb the stairs for each iteration. More plain language, like how do we calculate the distinct ways for each stairs. We will also use a unique named memorization to store and reuse the solutions to sub-problems. Like when we initialize the solution, we will create a space to capture all the solutions we already calculated in the sub-problems and let them ready for use in later steps. This is actually a key feature of dynamic programming, by which we can avoid redundant calculations and significantly improve the efficiency of our problems. Okay, we will go through 3 different kind of approaches today. The very first one we're going to do is we're going to use the recursion and with the cache function, the built-in cache function. And for solution 2, we're going to use a bottom-up approach using the tabulation, which is currently we are actually create the cache space by our Python script instead of using the built-in function. And for solution 3, we're going to achieve by iterative bottom-up approach. So for that case, we're currently just using a different ways to show how we can even save the space complexity better. Okay, let's tackle with our first solution first. So as we just mentioned, for the very first one we're going to do is we're going to use a built-in function, which is the add cache, to do our memorization. So by using the add cache function, it's simply just we added the add cache before the defined function climb stairs. And now we're tackling the how do we define the details for the climb stairs. So from here, most of the recursive function will currently have 2 mainly components. The first one is the base case, which is when are you going to stop the recursive steps. The second one is the repetitive steps, the recursive steps, which means how do we want to repeat it again and again, and how do we call the function again and again. So very first for here, we are going to do is writing the base case. So let's thinking about what would be the base case. So assuming you are actually starting from the ground, if there's no stairs, or we say the n is equal to 0, then the output would be what? be 0, right? Because you are just standing there, you don't need to climb anything. So if n is equal to 0, we are going to output 0. But what if the n is equals to 1? So if the n is equals to 1, then we are actually only have one option just to climb one step. Because even though you have like two options, you can either like climb one step or climb two steps. But since we are going to reaching to the top as the very first stair, so you don't have to actually climb two steps. There's not a available option. So if the n is equals to 1, then we will say the we will still like have the output as 1. So the best case would be if n is less or equal to 2, we'll just return like n. So we didn't like go through if n equals to 2. So if n equals to 2, there are two ways, right? The first one is for each time we climb like 1 steps, and if the second choice is we just directly climb 2 steps to reach out to the top. So these two are the options we have, and these two are the only like distinct ways we have. Then there's how many options? Very easy, right? 2 options. So the output will be the 2 itself. So if n is less or equal to 2, we just need to return like n. And the second part is we are going to do the repetitive like steps. You can either like write the repetitive steps out of there and have a result somehow, and then at the end return the result, or you can just directly to say like we want to return self dot climb stairs. So by this way, you just repeatedly call this function repetitively to going deeper and get the base case. And for each like level, we're going to compare is how do we capture or how do we calculate the distinct ways we can climb to the top. Remember when we're talking about the core like ideas of the the thinking of the dynamic programming, the thing is how we break the whole problem into the sub problems. So for this particular case, we're going to think like how do we calculate the distinct ways for each stair or each like level of the stairs. From here we can see like if we actually say it backwards, like when we on the like stair, maybe I will say just stair n, then how many distinct ways here? Actually, if we climb into the stair n, there are two options we can do. The first one is we are climbing from the stair n minus 1 and just climb 1 steps, right? And the second one is we're going to climb from the stair of n minus 2, and we are going to climb 2 steps in this iteration. So actually what we can do or what we have for this option is only 2. So the only 2 option is we either climbing 1 steps from stair n minus 1, or we climb 2 steps from stair n minus 2. So of the whole distinguished number of the steps here is actually based on what we have for the previous like 2 stairs. So if we have a number like we have a distinct number for stairs on the stairs of n minus 1, and also have the distinct number for the stairs on the stairs n minus 2, then what we need to do is just basically add them together. So like we have n like distinct stairs of n minus 1, and then we have another amount of distinct ways for stairs on n minus 2, then both add them together, we will get our distinct ways for stair of n. So that is our approach, and the retrieve steps is more like a sub-problem, so we can repeatedly to calculate no matter which like stairs it is on. When we're looking back, we always look at the same thing here. So when we convert this part to the coding like language, we'll just to say return the self.climb stairs, and for the very first component is on the stair n minus 1, and the second one is we're going to call like the climb stairs again. Oh, I might like misspelling here, I'm sorry. So we have the self-climb stairs, and then the second component would be n minus 2. So we have these two options, and all the way we're going to recursive down to the bottom level, which is n less or equal to 2. And after that, when we reach out to the bottom, we will always from the bottom to the up level to get all the way to the top. Reach out to top and get the final answer for how many distinct ways we can reaching out to the top. Okay, let's submit the problem, the solutions, and it's already accepted. So our solution, just make a success, right? So from this approach, actually, what we have here, for the time complexity, we have that is as big O of n to 2. So why is that is big O of n to 2? So n is because we actually have n numbers, so basically we're going to go through them. But from here we can say like we're using the cache function, and we don't need to like calculate each level, each when we like see a number, we don't need to calculate multiple times. So that is not a 2 to n like exponential approach, but still we're going still through the going through the depths to say how do we calculate the each level of there. The depth there, it would be n like depth there. So we will be have the time complexity as O of n to 2. And for the space complexity here, since we're going to using the cache like building function, even though we didn't create anything here, the building cache function will always still have some building things here, like building a space to install all the immediate data in the between of the the recursive steps. So the space complexity will be O of n. So this is our first approach, and then now we are going to just for our like second solution. So for the second approach, actually we don't need to using the building function. What we need to do here is just we create our own like space to install our like sub problem solutions in the between. So what we have here is we create a space called DP, because this is dynamic programming problems, right? And we have the space initially all the way to 0, and for the space length of for I in range of n, because we are going to say like at the very beginning, I don't know like how many distinct ways for each stairs, so I just need to do is initially everything in with 0. And the second thing is we're going to just modify the base case a little bit here. We talking about like when we have the one stairs, so we only have like one options, because we just need to climb one steps, that's it. And for the second one, when we go into the stair 2, we have like two options. The first one is we climb twice, and each time we climb one step, and the second choice is we just climb 2 steps there. So there's also like just one option plus one option would be 2 options. So you may get a little bit confused about like when we're talking about stairs, we say like 1 and 2, but when we come into here, the index is 0 and 1. Actually, this doesn't matter, right? Because the concept, their logic is just there. The only thing difference is how do we memorize, how do we calculate, how do we store, how do we memorize all of the information there. So if you feel like more comfortable to say, I just wanted to meet like the index match to the stairs number, then you can just create a even larger like DP space, just maybe one more, and you can just store the DP like from the stairs number equals to the index number. But from here, I just keep my very original like choice. I just need to say like for the index, we're starting from 0 instead of starting from the stair 1. Okay, the second part is we're doing those repetitive steps. So since we know like for the very like lower stairs, how many like different options we have. So in this case, we just kind of like a little bit like from the top down like ideas and convert that to the bottom up like options. So from the bottom up, we always know the smallest number, so we just need to go some one stairs further, and then we know like if we're going to step like stair 3, we just need to calculate the combination, the sum number of the dp of 0 and dp 1, which stands for the distinct width on stair 1 and the distinct width on stair 2. Then we combine them together, we will know like how many distinct widths on stair 3, right? So from here, what we just do is for I in range of for I in range of 2 to n. So why is 2? Because we already know what is the base case for 0 and 1, right? So we just need to starting with 2, and we have the dp I equals to dp of I minus 1 plus dp of I minus 2. Basically, we have the exactly same idea here, just like it's depending on the 1 step lower and 2 step lower. So when we know the distinct weights on the previous stair and the stair before the previous stair, then we just combine them together, we will get our like distinct weights on current like stairs, and we can calculate all the way up to the top, which is n minus 1. So still here again, we didn't actually meet the index equals to the stair number. So if we say like n stairs, that actually is meeting the n minus 1 in the dp environment, right? We just had some tricky and play around with the index and the number there, but if you again feel more comfortable, you can always like meet or we say set the index equals to the stair number. Okay, coming back to the solution here, so after the for loop and we go through all the iterations there, we're reaching out to the all the way to the top, right? And the last thing we need to do is just we return the dp space calculation result we calculate for the step n minus 1, then we will get our like expected output. So just submit our like results, and it's still also successfully. So from here, we didn't changing any of the time complexity or the space complexity, because for the time complexity, you will just always like go through the part, but from here you don't need to like do the recursive things. You just need to for loop and go through the n numbers. So for here it's more like we increase time complexity, or is it not increase, it's just kind of reduce. So we improve the efficiency and reduce the time complexity to the O of n, because we just need to do a for loop and go through each number here. So the time complexity, I probably have some like mistalking earlier. If I say that is the same, then that is my fault. But we keep the correct answer here. So for this solution, our like time complexity will be O of n, and for our space complexity, since we create the dp space to install the always memorize the intermediate like answer, then we will say the space complexity will be O of n. So both of them are O of n. Okay, this is our very second like approach, and then now we can go to our very last approach. Is we are seeing like how do we even push our optimization a little bit further, right? How do we kind of improve our either the time complexity or the space complexity? Because since we're going to calculate all the things way up to the n stairs, then it's hard for us to improve the time complexity, but somehow we could still improve our like the space complexity, because when we create the dp environment, actually for each sub problems, it only cares about the one before it and the one before the previous one, right? So what we need to do is we just need to keep the current like value and the previous one and the one before the previous one. So only 3 values we need to keep in mind. In this case, we're going to create 3 variables. The first one is current. The second one is previous, probably we say 2, like 2 steps here. And the last one is previous 1, which is equals to 2. So previous 2 means the one, like the difference between the previous ones with the current one. So previous 2 means there's 2 steps between the previous one with the current one. this previous one means the one just before the current one. And we're still going to go through the for loop iteration. So we say for I in range of 2 to n. And what we need to do here is we calculate the current first as the previous one. So exactly the same thing we did. But for next iteration, we were going to change in the positions, right? So previous two, actually the previous one will becoming the previous two because we're kind of moving forward a little bit, and the current one we just calculate will be the previous one, just before the next current one we're going to calculate. So we need to add these two steps to make sure like we always know for next iteration we always know what is the previous one and the previous, the one before the previous one's number, right? After the whole for loop iterations, we go through all the numbers up to the top one. We just need to do is just return the current value is what we want here. So we submit again and we are finished this solution. So from here we can say like the time complexity, we say that we are going to go through all the stairs. So the time complexity will not be changed. It will be still be O of n, but the space complexity, since we're going just to create, we say like the 3 variables here and we didn't using any other like space. So 3 means constant. If we say constant space complexity, that will be O of 1, right? So we can reduce the space complexity from O of n to O of 1. Okay, let's submit again. Oh, I'm sorry. I don't need to submit, right? I just submitted before for the solution 3. So, but anyway, I don't like to see the running errors. I submit again here. So this is our very third like approach, and basically this is a very the best options we can have. This is the most optimized solution we can have. But if you like show the previous like solutions in the interviews, that might be okay for some of the interviewees, but they may also ask a follow question like how can you just improve your solutions or optimize your solutions there. So you may still eventually come into the very last one, but from the learning purpose, I think we still need to go through all of the solutions here, and that will be help you to understand what is dynamic programming and help you to practice your Python like coding languages. Okay, thank you everyone, and I think that should be all for today, and hopefully my videos help you to solve these problems and help to get a better understanding on this particular like problems here and the solutions here. So if you have any questions, feel free to just make comments down below, and if you do like my videos, please give me a thumb up, and if you are new watcher, new friend for my channel, please do subscribe my channel, and we will see you in next video. Thank you.